This is Lab 1, the Constant Velocity Lab. For this lab, I made a video of an object moving across a table. This object had constant velocity. I then analyzed this video using Tracker and was able to come up with a computational model. In the process, I analyzed physics principles, including Newton's second law, and made a comparison between the predicted and observed data from Tracker and the computational model and made it into a plot. The video that I used was a Lysol can moving across a table at constant velocity. From this video, I analyzed some results. The start time was at 0 seconds and the last time was 1.002 seconds. I was able to find the initial position of the can from Tracker with the values that were given. The ball initial velocity was calculated from the formula velocity equals change in position divided by change in time, which all the values were taken from Tracker and the values that were given. This is part of the computational model that I created. As you can see, the ball mass was what I found online for the mass of the Lysol ball, and then I plugged in the values from the last slide for the ball position and the ball velocity, and also started the time at t equals 0. The fundamental principle used in this lab, as discussed, is Newton's second law. Newton's second law is velocity final equals velocity initial plus all the forces times delta t divided by mass. The computational model seen below is how I implemented Newton's second law into VPython. For VPython, I used a while loop, and this was in the while loop, so the ball velocity equals the previous ball velocity plus all the net forces combined divided by the mass times delta t. I then used the position equation, which is the ball position equals ball position from previous plus the ball velocity times delta t. The while loop also shows that net forces that were used in this experiment. The net forces seen in here are 0 because we're at constant velocity. This is proved by V final equals V initial plus 0 forces times delta t divided by mass. Thus, this reduces to V final equals V initial, proving that there was constant velocity. The images shown here are from the computational model, and these are shown when the computational model is run. The top one is a graph from VPython, and the second one is an animated image, also calculated from VPython. This is a plot of the model of experimental position versus the model position, and is a position versus time graph. So as you can see, the predicted value from VPython was negative 0.77058, and the actual value of the position was negative 0.758. As you can see, there's not a huge difference between the two. There's only a 0.02 difference. It may seem like there may be a larger difference based on the graph, but if you look at the increments that the graph goes by, you can see that it's very minimal. The error calculated from this experiment may be human caused. This is shown by the variation in the y-axis. When in Tracker, you have to place the middle points on the Lysol can, and this may not have been always at y equals 0, thus there was fluctuations. So what if the axes were flipped on the graph from Tracker? And what would happen was just discussed in the last slide, is that this is a y versus time graph, and because y was not constant, y is going to fluctuate back and forth, as you can see in this graph. So what does this mean? It is not possible to say how many pushes or pulls are added together to give 0 net force in this case, and this is because we have not taken into account the friction that were caused by the Lysol can and the table, and also gravity that's pushing the Lysol can onto the table. In conclusion, this lab was a constant velocity lab, and we used VPython to predict what the motion versus time would be, and we then plotted the time of the motion that was actual and predicted on one graph.